Alright, at the end of the last video I was again cut off, so quick summary of what's going on here. We have the centroid x bar here is found by adding together the moment of each of the different masses affecting the system here. So we have n different masses, each one of them has a mass and a position. We add up their moments, mass times position, from 1 to n, divide by the total amount of mass in the system, which we usually just call m. So add up all the masses together and you get the total mass m, and that will tell you your centroid location. So it's kind of like that weighted average for each of the positions to figure out the x bar. Now, all of this was assuming that all of your masses lie along the x-axis. What about if we go a step larger and we look at the two-dimensional case? So we now have an xy plane. And now in this xy plane, we have a bunch of point masses that are in different locations. So we might have something like up here, and then over here, and then on this side. Just for the sake of the picture here, I'm going to do these three different masses. So we'll call this M1, M2, and M3. And each of these now has not just a single position, but an xy coordinate pair. So we've got x1, y1, x2, y2, and x3, y3. Okay, so now, instead of just finding the single point that everything the single x value that everything kind of averages to, we're now looking for an xy coordinate pair that would balance the three of these points all at once. So you can imagine that there would be like some little connections that have no mass at all, but just kind of keep these 3 points in a single plane. Imagine that they can't move independently of one another. They're all sitting there in this plane. We want to find what point could balance this entire shape here. That's the question. So some point in here should balance this. And one of the ways that we're going to figure this out is we're going to talk about the moment of this shape with respect to the x and the y axis. So imagine now that we have our laminate that we're interested in here, and we're not just trying to balance it on a point, we're trying to balance it on a line. So you try to find a line, something like this. There we go, where it will balance all along that. Now, in this case, there's an equal amount of moment on each side of this line. But if I were to scoot this over to one side here, you can see that it immediately always topples that direction if I were to unbalance it. So the moment tells me how likely it is that that's going to happen. So as an example here, if I draw the y-axis here, imagine that we balance this triangle on top of the y-axis the way that it's sitting here. Which way is it going to fall? Is it going to fall to the right? Is it going to fall to the left? It's going to depend on these masses and their specific coordinates. And so what we're doing is we're finding the moment with respect to the y-axis. If that moment is exactly 0, this shape would balance. If the moment was positive, we would fall off to the right side. And if the moment was negative, we would fall off to the left side. Okay? And then we can do the same thing with the x-axis afterwards. But let's figure out what the moment with respect to the y-axis is. Well, in order to do that, we're going to look at each of these 3 points separately. So start with M1 up here. If I want to figure out the moment of M1 with respect to this axis, I need its mass, which is M1 itself, and I need the distance to this point that I'm wondering about rotating around. So I need this horizontal distance here, which is going to be exactly x1. And so the moment of this first point with respect to the y-axis is going to be m1 times x1. Okay? Then the moment of the second point with respect to the y-axis is going to be calculated almost the same way. We'll take m2 times this horizontal distance, which is now x2. And over here, we'll take m3 times this horizontal distance, which is x3. And because x3 here is a negative, it's going to count negatively, and it's going to counterbalance these other guys. So the total moment with respect to the y-axis is going to be adding these moments up for each of these values in the system. So the moment with respect to the y-axis is going to be m1x1 plus m2x2 plus m3x3. And of course, if there were more points in the system, you could just add on more terms. We're just going to add up the moments of every individual point in the system. And so in general, the moment with respect to the y-axis can be found by taking the summation from I equals 1 to n of mi times xi. So that is the moment with respect to the y-axis. Then to find the moment with respect to the x-axis, we're going to turn our focus to the x-axis here. And we're going to imagine whether this triangle is going to balance up or down if it were balanced along the x-axis here. So now we're going to measure the vertical distance from each point to the x-axis here. Now this one, again, we're going to have the same mass, m1, but now the distance to the x-axis here is going to be y1. For m2, the distance to the x-axis will be y2. For m3, the distance to the x-axis will be y3. And so the moment with respect to the x-axis is going to be m1 times y1 plus m2 times y2 plus m3 times y3. And in general, if you had a bunch more of these points, you could find the total moment with respect to x by adding them all up from I equals 1 to n mi times yi. So this is reverse of what it might immediately look like. We have the moment with respect to the y-axis involves the x variable, and the moment with respect to the x-axis involves the y variable, but I hope we can see from this picture why exactly that's the case. Okay, so now how do we figure out the centroid? Well, these moments here tell us how far off one side or the other we are from the axes, right? So if we have a positive moment with respect to the x-axis, that means there's more moment up above here than there is below. So that means that the centroid must be above the x-axis, right? That's kind of the idea of what the centroid is. To find the balance point, it would have to be somewhere above. Same with the y-axis. If the moment with respect to y is a negative value, that means there's more mass pushing down this side. It means that the centroid is going to be off to the left. So these moments are telling us actually about where the centroids are, and we can find the centroid with a very similar calculation. We take the moment with respect to y, divide by the total mass of the system, and you are going to find the x-coordinate of the centroid here. Take the moment with respect to x and divide by the mass of the system, and you are going to get the y-coordinate of the centroid here. So we have like separate weighted averages for x and y values to figure out where these are going to be. So in the end, x bar, when we're rotating around the x-axis here, I guess I should do this in yellow, x bar can be found by taking the summation of all of the I have it right here. The summation of all of the mi's times xi's and dividing by the total mass of the system. Or in other words, we take the moment with respect to y, my, and divide by the mass, m. And that's how we find the x-coordinate of this system here. Then, on the other hand, I've actually gotten my colors backwards. This one should have been the blue one because it involves all the blue terms here. So let's call that one blue, and that matches up to all the blue values, blue all the way along. Then for y, this one actually should be in yellow. The y bar, the y-coordinate of the centroid can be found by taking the moment with respect to x and dividing by m. So we have the moment with respect to x divided by m. So again, add up all of the moments, add up all of your moments with respect to each of the y values, and then divide by the total mass in the system to find your y bar. Okay, so that's the end of this video. In the next video, we're going to actually use this calculation method to find the center of mass of a system of point masses.